Now let's look at the mod 8 tables. As with the mod 7, both the addition and multiplication tables are symmetric about the main diagonal. Moreover, for addition, each row is a cyclic permutation of the top row. For example, 5, 6, 7, 0, 1, 2, 3, 4 is a permutation, a cyclic permutation of this. We've moved it to the left and taken these 5 numbers and then put them on the right. And this has given us this row here. And similarly for all the other rows. And this is going to be true for all mod tables. And the proof is essentially just from the definition of addition. Multiplication, however, behaves somewhat differently in the case of mod 8. And the essential difference comes from the fact that 8 is not prime. And as before, we usually omit the row and column of zeros. So now let's look at the various rows, and we see that in the case of 1, 3, 5 and 7, that indeed each of these rows is a permutation of this top row here. So for example, let's take this here, 5, 2, 7, 4, 1, 6, 3. 1 occurs down here exactly once, 2 likewise, 3, 4, 5, 6, 7. So it's not a cyclic permutation, but it's a permutation of this in the sense that every element here occurs once and only once in this row here. A second point is that in the rows corresponding to A is equal to 2, 4 and 6, we have occurrences of 0. So in particular, that means that there are elements which when multiplied by 2, 4 and 6 respectively, and these elements are not 0, these numbers are not 0, the result is equal to 0. We sometimes say that 2, 4 and 6 are divisors of 0. And these are the numbers for which the greatest common divisor of A and N is not equal to 1. The essential point, as I said before, is that 8 is not prime, and the good rows are those rows corresponding to numbers A, 1, 3, 5, 7 in this case, which are relatively prime with 8. In other words, such that their greatest common divisor with 8 is equal to 1. And something similar will happen in the case of all non-prime multiplication mod tables.